Okay, so let's start. So let's start the second tutorial of the day. So we're very happy to have Professor Jim Luedtke to do this second tutorial. And the presentation will be on the stochastic integer program. So Jim, you have the floor.
All right, well, thank you again very much for the invitation. It's my pleasure to be here and hopefully, help you get to know about this area a little bit more. So I'm going to start right away with, if I get to change my slide, just with kind of a motivating example before, even defining some notation, just to kind of get us thinking about the types of problems where stochastic integer programming might be useful. And so one application area that I have a lot of interest in is in energy. And so kind of a long-term planning problem in energy is somehow a generation and transmission capacity expansion. So the idea here is you're thinking, maybe for the next 10, 15, 20 years of installing maybe new generators, and you need to determine maybe the type of generator, whether it be wind or gas or something like that, and the locations. Maybe you're also deciding on transmission line connections between things to go along with that. And so, the question is, where should you do this in order to minimize sort of the first of all, the capacity, the expansion cost itself, but plus also the operating cost, given that becomes your new sort of system design. And so two major features of this problem that motivate the use of stochastic integer programming is, first of all, there's discrete decisions, like you either install a generator at a particular location or not, and likewise for the transmission lines. And then there's certainly uncertainty, right? You're looking about 20 years into the future. You're not even going to know for sure what will be the demands or the loads in different locations. Certainly weather is uncertain, and even, on a given day, right, there would be, weather variability in terms of the yield you might get from different, for example, renewable resources like wind turbines and things like that. So if you want to, sort of dive into this example a little more, and this will be useful for starting to set up notation and things as well. We could first sort of imagine a deterministic model, where you just imagine that we assume everything is kind of known for the future. And then, the way this model might end up looking in this case is you would have a set of candidate generators. So we'll call those G, and maybe you have some certain demand locations J. I'm going to abstract out in this version of the model transmission just to kind of make it simpler. So I'm just going to talk about sort of meeting the full demands. And then if we install a particular generator, there's a fixed cost for the installation. And then we'll assume, and this is the part that is certainly not realistic, but we'll assume we know a particular load dj for every demand location j. And then, as I mentioned, we have these binary decisions. So xi for each possible generator, whether or not we would open that or not. So those are these discrete variables. And then once we've designed the network and we have the available generators decided, then there's this kind of operational decisions of saying, okay, well, how should I meet demands in the best cost way? So I could do that by defining variables yij, which is basically how much demand at location j do I meet from facility I. And for reasons that'll become clear later, I'm also going to sort of build into this model that I assume that I can shed some location or shed some demand at certain locations. So if it's too expensive to meet all the demand at a particular location, I assume I can shed that, but of course I'll pay a penalty for doing that. And so putting it all together, the model then becomes something like this. I have my minimizing my total initial costs plus the operating costs, which have this component here, which is based on that sort of cost for meeting demand from different locations, and then plus the penalty I'm paying for some load that I did not meet. And then for each of my demand locations, I either have to record that I didn't meet some of the demand or I'm otherwise meeting the demand. And so I get these equations. And for each generator, I have these constraints here that are saying, first of all, if I don't build the generator, if xi is 0, then I shouldn't send any energy from there because I don't have it available. So that would happen if this is 0. Otherwise, if I do build it, so the xi is 1, then I have a capacity of ci from that generator. Okay, so this is a sort of a basic deterministic mixed integer program. You could give this to your favorite solver. By the way, Walter, or anybody, if somebody posts a question in the chat, I'm not going to be very good at monitoring that. So please just go ahead and interrupt, and you know, it's a tutorial. Questions are welcome throughout. So, but it'll be helpful if somebody lets me know.
I'll deal with the
okay.
the
Thanks. Okay. So okay. So this is a deterministic model, but what would be, you know, how would we handle this to deal with the fact that actually in reality there's a lot of uncertainty here. So in particular, the demands would be uncertain in this model, and also the capacity, right? If you think of the some of the generators as being like wind fields, a field of wind turbines, then how much, you know, output I'm going to get from that is also random. So you could think of that as being like a random capacity. And so the classic kind of two-stage stochastic optimization framework is where we're going to sort of take some of our decision variables and declare those as things we have to make as here and now decisions. And sometimes we call that first stage decisions. And in this transmission expansion, or this generator planning problem, it's very clear that it's the decision of which generators to install and where. That's the here and now decision. That's the thing that we're trying to actually decide now. But then we're going to assume in this two-stage framework that after having fixed those things, then we observe all the randomness, right? So we pick a day, you know, 10 years from now, and we observe how much demands there are, and we observe how much wind we get. And then after having observed all that, then we're going to sort of operate our system in the best possible way. And we call these our recourse decisions. So we make these decisions in response to those observed random variables. So we call those recourse decisions, or sometimes second stage decisions. So our goal is to choose our current decisions so that we minimize those immediate costs of those, plus the expected value of kind of the best response we'll make after having observed those random variables. So here I talked specifically about expected value. There's certainly a lot of interesting work on dealing with risk-averse objectives or things like that. But for the purpose of today, we'll ignore that. And so in building up this two-stage model, you have to sort of differentiate which decisions are going to be those here and now decisions and which are going to be those recourse decisions. And so as I mentioned, I'm going to go back to this kind of generation expansion example. So here we're going to consider the loads at different locations as being random. So capital DJ will now denote that those are random variables, and also the capacities at the generators, right? So CI will represent those random variables. Our here and now decisions are going to be those binary opening decisions for the different generators. So we fix those now, and then we have this system that we can operate. And then on a particular day in the future, we're going to get a random observation of the demands at all the locations and the capacities of all the locations. So I say the wind generations or the solar generations. And so our model is going to look like this, where we're going to, at the first stage, we're choosing those binary decisions of which generators we're building. And we pay the fixed cost right away for that. And then we're going to add to that the expected cost of the future. And I didn't build it in here, but you should imagine there's probably some sort of factor here to factor in sort of the time value of money that this is repeated over and over. But the main thing I want to highlight here, the interest here, is that this is an expected value of this function Q, which is kind of an implicit function that's telling me, given that I chose this design, I have these generators available, and then I observe this vector of demands and this vector of capacities, what's my minimum operation cost? Okay, and so that's this linear program down here. So now the first stage variables X are fixed, and also the demands and capacities that are fixed. And then I have this problem that looks quite similar to the deterministic problem that I wrote down, except that now the X variables are fixed. Okay, so this is determining the minimum cost way to sort of operate my system under these conditions. So generally, the sort of general model that this is an example of is a two-stage stochastic mixed integer program. And so here we have some first stage variables. Generally, they're X, so they could be some continuous variables, some integer. We'll have some linear constraints, some first stage cost. And then we also add to that the expected cost of our sort of best response to what's happening. And so for the general model, like C represent all the data that might show up in this recourse problem. And that is going to be the random sort of vector that's happening. And then in this case, for the recourse problem, in the example I showed, the recourse was all continuous, and that's kind of a special case that's nice, and I'll talk about that in a little while. But generally, we'll also be interested in cases where some of the recourse decisions also have integer variables. Okay, so that sort of makes it a two-stage mixed integer program with integer variables in both stages, kind of the general case we'll consider today. So I gave that one example application, but just to kind of highlight that there's many applications of this framework. And you can imagine anytime you bring together the power to model discrete decisions and to handle uncertainty, you can capture a lot of realistic things. So the first example here I'll highlight, again, in the energy area, is something known as the stochastic unit commitment problem. It's a little bit of a shorter term planning problem where you're looking ahead maybe just a week. And you're thinking about, okay, still have randomness in the loads over the next week, and in particular, maybe in my forecast of how much wind or solar production I'm going to get. And then I have these decisions of not which generators to build, but which ones to turn on. There's a sort of commitment aspect that you have to sort of pre-plan which generators you want to have on and off throughout the week. And so again, that's kind of a binary decision. And then given those decisions, then as the week goes by, you make these sort of reaction decisions, how much you're actually going to produce. Maybe in some cases you can sort of do line switching in your network, which would be an example of binary variables happening in that recourse phase. There's some really nice example applications that Lewis and Taimo and co-authors have been working on in wildfire initial response planning. And here there's, the random things are, well, where are these fires going to be happening? What's going to be the locations? How big might they be? And in this case, or one of the models I remember reading from their group is the first stage decisions were pre-positioning equipment. So these were sort of integer decision variables saying how many bulldozers should you put in a particular location. And that certainly is a discrete decision because you're only talking about 3 or 4 maybe of bulldozers in different locations. And then in the second stage, once you've observed that a fire broke out, you have this question of how should you optimally deploy resources to try to do a good initial response to that fire. And then, of course, there's classically many sort of stochastic vehicle routing, any kind of transportation problems you can imagine have both random things like random customer demands, but also discrete decisions for doing the routing. So I won't get into the details there, but there's a whole slew of applications in transportation as well. So this is sort of a little bit of motivation that, okay, it's a general sort of problem class. It can be useful in a lot of different areas. And I'm going to focus now, shift a little bit towards how do we solve these types of problems. And so the first thing that we have to understand is what makes it hard. Why is it an area that we can't always necessarily just kind of give it to a solver and say, go, unfortunately, yet. And so there's sort of 2 main challenges to this, and they come from the fact that it's actually bringing in things from 2 different fields, stochastic programming and integer programming. So on the stochastic programming side, you have this expected value that showed up in the objective function. And even evaluating an expected value is a hard problem. It's a multidimensional integration problem in general. Even if you have a finite scenario approximation, which we'll talk about as being a common methodology, it might be a very, very large number of things that you have to evaluate. So the second challenge comes from the fact that you have discrete decisions. So that brings in integer programming here. Typically, if you're talking about realistic design or planning problems, you might have a huge number of these discrete variables. And so the combinations of them, of course, grows exponentially. And then the other part of this is that with integer programming in general, what you really need to be careful about is if you build a formulation and sort of the natural relaxation of that you solve is weak, it's not close to the true optimal value, then as you start trying to do some kind of enumeration process, that can blow up. And it becomes sort of hopeless to solve. So we have to sort of balance these 2 challenges within stochastic integer programming. And so now that I've kind of gone over the general framework and the problem, I'm going to sort of talk overview what we're going to talk about in this tutorial. So I'm going to start with a very brief description of one key technique. It's sample average approximation that helps deal with that kind of expected value issue that I talked about in the first challenge. And then that's going to lead to a certain approximation problem that has, fortunately, a finite list of sort of scenarios that we have to consider. But still, that list might be large, and that's going to be potentially still a difficult problem to solve. And so I'm going to talk about different methods for how do you solve that problem. Now, unfortunately, there's going to be a lot of really interesting things related to stochastic integer programming that being realistic in 70 minutes, there's no chance I'll be able to get into. So I'm not going to talk about multi-stage or risk aversion or chance constraints or distributionally robust things, even though those are all things I think are really interesting, just sort of limiting the scope here today. Okay, so let's talk about that first stage, or that first challenge. And so remember, this is kind of my general form of this two-stage stochastic program where I have this expected value of my optimal recourse function showing up here. And so in general, we have, this random vector C could be high dimensional, like we talked about. This could be demands at various different locations in my network, or capacities at different wind farms. And so in general, this is a high dimensional integration problem. And even if I fix a particular candidate solution X, evaluating that expected value can be a challenging thing to do. And what's worse is we need this not just for a particular X, we're optimizing over X. So you can imagine we actually would want this approximation to be good over a wide range of X's that are candidate solutions to this problem. So there's actually a very sort of simple thing that you might do that you can imagine doing. I mean, the engineers have been doing this long before this was sort of studied as a mathematically justified thing to do. It's sort of sample average approximation. Okay. So the basic idea is I have this random variable C that shows up in my expectation. That's the thing I'm taking the expectation over. And what I do is it's just take Monte Carlo draws from that random variable. Let's say they're independent, identically distributed for simplicity here. And so each of those, I take capital S of those, and I label those CS. And I then build a sample average approximation. Okay, so instead of having that complicated expected value term, which is over the full distribution of these Cs, I replace it with this sample average. So I just sum up over those scenarios, I'll call these different values that I get, this Q evaluated at that particular scenario and divide by the number that I had there. And so what I've done with this sample average approximation is I've replaced that expected value term, which would require this high dimensional integration, by this sort of finite sum. Okay, and it turns out that with this finite sum, which we'll see in a minute, I can now actually take my stochastic problem and transform it into a deterministic problem, but it's going to be very large scale. Okay, so we'll see how that transformation happens in a little bit. But for now, I would just want to sort of understand, well, what's the cost of doing this approximation? Is that something that's reasonable to do? And so, a key question is how many scenarios do you need to have, quote unquote, a good approximation? Okay. And so this is something that, of course, is, there's been a lot of research into this, and so there's a few citations there, but there's many more papers related to this. But the key takeaway that under certain mild assumptions, doesn't hold completely, but under certain mild assumptions, roughly the number of scenarios you need is on the order of the number of first stage decision variables that you have. So that's N1, if you didn't catch that notation. It's the number of first stage decision variables, and then divide by the accuracy squared. Okay, so epsilon is sort of the error you're allowing. So it's 1 over that squared, then times the number of first stage decision variables. There's other terms in there that I'm hiding, but in my mind, in terms of understanding the limits and ability of sample average approximation, these are the key terms to look at. So the good news is, and this is the thing that's kind of amazing, is that this sort of scales well, first of all, with the number of decision variables. It only depends on the first stage decision variables and linearly on that. So that's pretty good. And the dependence on the random variables is only kind of implicit. It's one of the constant terms. The variance of that will come in there. But in particular, it doesn't always sort of come up that it's sort of exponential in the number of random variables. So it's certainly not growing up as you might expect, like you would need if you were doing sort of a full exact evaluation of the integral. Okay, so this is a huge savings and really good news. Now, the bad news is if you want to get really high accuracy solutions, so if I want to make that epsilon very small, you have this 1 over epsilon squared term there, and that's going to make the number of scenarios really large, right? So that's the bad news, and that's inherent in the fact that we were doing kind of a Monte Carlo approximation. This is sort of what you could hope to get out of such an approximation. And so the conclusion that I draw from this is, as long as you're willing to accept modest accuracy solutions, so I let epsilon be like 5%, or maybe 1%, then I'm, not getting terrible with the number of scenarios that I need. If I would try to, push epsilon down to 0.0001, then, sample average approximation is not going to be suitable. Okay. But if I'm willing to sort of accept modest accuracy solutions, this methodology can work very well. In my opinion, this is just in my opinion here, so take it with a grain of salt. I think that in these types of applications, going for very high accuracy solutions is anyway kind of pointless, because remember all the assumptions we're going to build into this model. Think about that generation expansion problem model. I'm building some distribution of what I think loads and capacities will be 10 years in the future. I have to make all kinds of approximations of costs and things like that. So getting very high accuracy solution to a model that's going to have all these approximations built in any case seems unnecessary. And so that's kind of, that seems to be often the case for these types of applications where stochastic integer programming is going to be useful. So I'm going to take for granted that this building these sample average approximations will get me to solutions that are good enough for the sake of making good decisions here. And so we're going to transition to the next challenge, which is how do we even solve that sample average approximation problem? So it's still going to be a challenge remaining there. So this is, the scenario where we're doing a sample average approximation. And so I've taken these scenarios, CS are sort of the samples that I obtained when I did that sampling. And now where I had previously had this expected value, I'm having this sample average function. Okay, so this is sort of replacing that. So this is the approximation problem that I want to solve now, where for each scenario S, again, I have this kind of recourse function that's evaluating that here. And so the first thing that we could do is we could take, and for each one of these scenarios, we can introduce a set of variables, I'll call them YS, which are basically kind of, well, what would I do if that's the scenario that happens? Okay, so and it's because now I have a finite number of scenarios, I can actually list that out and kind of pre-plan for every possible scenario that's going to occur. I'm going to make my decision to say, okay, this is what I would do in that recourse option. Okay, so that has this index S, those variables, because that's sort of specific to say, I would do that if scenario S is what occurs. So by introducing those variables, now we can actually sort of take this problem and put it into one big equivalent deterministic integer program. Okay, so that's what this is going to do here. So I have now my first stage costs, my first stage constraints, and I have that sample average here, but what I'm doing here is I'm plugging in directly the cost of the second stage decisions for each of the scenarios S. And then in my constraints, so what I'm doing is I'm repeating the constraints, those recourse constraints for every scenario, where in each one I use the same set of first stage variables X, because that's not allowed to vary with scenario. But for the parts that depend on the recourse decisions, I'm using the variables corresponding to scenario S. Okay, so that's how I can allow those to adapt to each different scenario. And then what I obtained then is this giant integer programming problem. Okay, and that's equivalent to that sample average approximation. And because now this is an explicit problem, I can give this to my favorite mixed integer programming solver. It could be a commercial solver or Skip or something like that. Let's see. Oh, sorry, I'm a little bit.
Say that, we can pick you.
I'm just checking the chat now. There's a good question here I do want to clarify here. Thanks, Goban, about the. So there's a question about, are the results true of continuous and discrete problems both? And are there tighter results for continuous problems? And I assume this was when I was talking, let me go back, about the
Take my check.
Approximation results here. So something along.
Yes, that's right, Jim. Thank you.
Okay. Yeah, thank you. Sorry for being a little slow to catch that. And so let me go to the results there. So these are the main results. And surprisingly, I find that the at this order, in terms of it being, the order of the number of first stage variables and 1 over the epsilon squared, this actually doesn't change much, whether it's continuous or discrete decision variables. And it turns out actually, what you can get is actually slightly better results in the case of if all the first stage variables are discrete. So technically you have a sort of a finite feasible region, even if it's exponentially large, you get slightly tighter results in that case. So the case of discrete decision variables, get you slightly better results in terms of these convergence analysis. But the broad order of things doesn't change that much in terms of the results that I've seen.
Thank you.
Sure. And I appreciate the question. I'm sure other people have the same question, so this is good. Okay, so just to go back to the example though, so this is the general purpose, or the general way you would write one of these deterministic equivalent forms. For that sort of generation expansion example, this is what that would look like in that example. And so what I would do is my first stage variable is X, which we're choosing which generators to build, that just stays the same, and that cost term stays the same. But then for all those variables that were based on different sort of scenarios of what might happen in terms of my demands and my capacities, I'm going to now introduce a scenario index on those. So where I had Yij now, it becomes Yijs, saying, okay, if this is what happens in the future, then I'm going to respond in that way. So it depends on the scenario S. Likewise for the shortfall variables, the Z's. And then all my constraints just sort of get repeated for all the scenarios now as well. Okay, so that's kind of what that looks like. And again, you can just give that to your favorite solver. So this is the first option. Okay, once I've done sample average approximation, I have a finite number of scenarios, I can take that and create what's known as this deterministic equivalent form. And the advantages of this is it's straightforward to implement. If I've written a deterministic model, then it's fairly easy to modify that to extend it to this two-stage stochastic program and have deterministic equivalent form that I can just give to my MIP solver. And the other advantage is this directly takes advantage of the fact that MIP solvers are getting better and better and better and being able to solve really impressive size problems. And so one should never, if you're doing stochastic integer programming, you should never sort of discount this option, right? Just give this, write the deterministic equivalent form down, give it to a big solver. These days, it's getting more and more likely it will just work, right? And certainly the easiest things to do. But of course, the limitation, and eventually there is a limitation, otherwise I wouldn't have more to talk about in this tutorial, is that the size can just still become too large. Right. So even though sample average approximation is good for giving me approximate solutions, I may still need a large number of scenarios to get a reasonable approximation. And if you look back at the example, when I write this deterministic equivalent form, what happens is I'm repeating lots of constraints for all these scenarios, and I have variables that are repeated for all these scenarios. And so if my basic problem was already pretty big, and now I'm kind of multiplying it all by the number of scenarios that I have, it can get really, really gigantic, such that maybe even loading the problem into memory is beyond the capabilities of current computers. And so the idea then is to move on to decomposition algorithms. So the idea there being we're going to solve a sequence of smaller problems, then try to sort of have an algorithm that brings the results of that together to hopefully converge to an optimal solution of the overall thing. So before we can sort of describe the stochastic integer programming decomposition algorithms, we're going to have to know a little bit about integer programming methodology in general, because we're going to have to understand how these fit into that. Okay, so I'm going to start off with just talking a bit about general integer programming. So if you're an expert in that, then you can sort of relax for the next few minutes. But let's just start off with the first general technique in integer programming is branch and bound. And really, this is kind of the basic idea for any exact algorithm for solving integer programs. So the idea is you start with some sort of a relaxation of the problem. In integer programming, typically it's the linear program relaxation, where what you do is you ignore some constraints such that you obtain a problem that's easy to solve or easier to solve. Okay, so the typical one being you ignore the integrality constraints, so you end up with a linear programming problem, which we can solve very well. And by ignoring some constraints, if I'm minimizing my cost, then by ignoring some constraints, I maybe can only get better. And so what I obtain as the optimal value of this relaxation problem is a lower bound on the true optimal value. Okay. And if I get really lucky, then if that relaxation ends up satisfying the constraints that I ignored anyway, then I could actually conclude, well, there's a feasible solution that also has that value, and now I know it's optimal when I'm done. But otherwise, and that's a typical case, is you'll have relaxed, say, the integrality constraints, and you'll find a decision variable in the LP relaxation solution takes on a fractional value. And so what you then have to do is divide the feasible region, this is known as branching. And so I might say, okay, well, this variable should be 0 in this one case, or I'll consider the other case where it should be 1. And now I create 2 new subproblems, and I basically just repeat that process recursively in this process. And then the idea, the key thing there is every time I solve this relaxation, if I get this lower bound for that relaxation and it's somehow already worse than some known feasible solution that I have, then I can prune it and not have to explore that anymore. Okay, so that's sort of the key way that this branch and bound process maybe avoids complete enumeration. And so it's a useful heuristic for thinking about how long does branch and bound take, is you can basically think of it as two terms. One term is how many nodes you end up exploring in this branch and bound tree. And the other term is, well, how long does it take to solve the relaxation of each node or to process that node? If you multiply that together, that's roughly the total time. And it turns out that both of these factors can be very important, and it's useful to think about this way to decompose the total time as you think about how different algorithmic choices impact those two factors. Okay? So in particular, in the case of stochastic programming, if you have a very, very large instance, even solving, say, the linear programming relaxation of a very large stochastic integer program can be extremely time consuming, right? Because it's a very, very large formulation. So time to process a single node might become a limiting factor in a situation like that. On the other hand, as the typical case in integer programming, even if you can solve a single node very fast, if you're not careful about how many nodes and how you're doing good branching within this and how you're doing good relaxations in this branch and bound process, that number of nodes can grow exponentially in the number of decision variables. And so, exponential growth, ends up destroying anything, right? And so you have to balance both, right? So the key to success is that you have to somehow be able to solve the relaxations fast, or at least fast enough. But also you have to keep strength of the relaxation. So they have to be strong enough so that when you start this branch and bound process, you have to be able to prune many of the nodes and avoid this kind of exponential growth of the number of nodes. So it's a tall order, especially in stochastic integer programming, to be able to do both of these well. Okay, so the other technique that we need to be aware of in terms of integer programming generally, it has to do with how do we keep control of the number of branch and bound nodes, is something known as valid inequalities. So basically, for a given set, say capital X, in this example, it's a set that's defined by some linear inequalities and some integer constraints on some of those decision variables. So it's a mixed integer set. We define something known as a valid inequality. It's basically just a linear inequality that's satisfied by every point in that set X. Okay. So very simple idea, it's just an inequality that's satisfied by all the points in the set. But the point is that we want to be able to derive some of these inequalities that aren't already known in the formulation. Okay, so certainly any inequality that's part of the formulation, say these AX less than or equal to B inequalities, those are valid inequalities by definition. But what we'd like to do is find some valid inequalities that hopefully will cut off some of the relaxation. So if we're thinking about the LP relaxation of this problem where we ignore the integrality constraints, then we'd like to be able to find valid inequalities that maybe cut off some of those solutions that would be allowed when we did that. So the goal of adding these valid inequalities is to improve that relaxation bound, ultimately allows you to prune nodes higher up in the branch and bound tree and take control and limit the number of branch and bound nodes you explore. So the key questions that are hugely studied in the integer programming sort of community is how do you find these valid inequalities? That's a very important problem. And then, practically, computationally, what's a good way to use these within a branch and bound algorithm? So in terms of finding valid inequalities, one thing you can do is you can study your specific problem, and you can think about formulating in different ways that lead to new inequalities that are redundant maybe for the formulation when you have the binary variables restrictions enforced, but would not be redundant when you ignore integrality and you look at an LP relaxation. Okay, this generation expansion example is a good example of that. So remember, I have these binary variables that are indicating if each generator is open, and these Yij variables indicating the demand at location J served from generator I. And in our formulation, we had constraints that looked like this, and this is for the stochastic formulation where I have scenarios S. But basically the constraints looked like this, where I said if a binary variable is on the right-hand side, so that was a 0, that enforced all of these Y's to be 0. and then it had the capacity otherwise, and that's scenario specific in the stochastic model. But what I can do is I can add these other constraints, which when the variables are binary value, these are redundant, but they might not be redundant when in an LP relaxation, when the variables X take on fractional values. Okay. So what's this constraint saying is just, I'm looking at individual Yijs variables. So how much am I serving to customer J from generator I in scenario S is less than or equal to this quantity times the variable Xi, where this is sort of, it's redundant if the CSI is what shows up here, but if it turns out that the demand is less than that, then this, it turns out not to be sort of a redundant linear inequality, again, in the LP relaxation. Okay, so certainly I can enforce this because I would never send more than demand to that particular customer. It turns out to be not redundant in the LP relaxation. So that's an example of deriving a valid inequality for a set of valid inequalities based on your particular problem application. In terms of finding valid inequalities in general, as I mentioned, this is a huge topic of research in the integer programming field, and a lot of that research has been built into commercial integer programming solvers, and that's what makes those so powerful. That's part of the reason why we can solve such huge integer programs now efficiently. So how to use these valid inequalities? Okay, so when we talk about kind of the main methodology for using valid inequalities is known as a branch and cut. And the idea is we're doing this branch and bound process to solve this integer program where we create a node by branching, we solve the LP relaxation, and then if it has fractional variables, we would maybe branch again. What we do in this case, instead of immediately going to branching when our LP relaxation has fractional values, what we could do is go to another subroutine and say, hey, can we find some valid inequalities that would remove this infeasible fractional solution? So if we can find such inequalities, and we'll call them cuts in that case, then we add those to the LP relaxation at that particular node and go back and resolve it. And this becomes kind of a loop process here. So we kind of do that, potentially that technique of trying to find and add these valid inequalities to improve this bound. Potentially we might do that at every node in the branch and bound tree. And that's what's known as branch and cut. And so why would we do this? Well, first of all, we hope that by adding these valid inequalities, we'll improve the bounds and then therefore have fewer nodes to explore. But what's relevant for solving stochastic integer programming problems, which we'll see in a little bit, is sometimes you need to add valid inequalities just to define the feasible region. Okay, and that's going to be relevant here once we start to see how some of these decomposition methods work. And this branch and cut approach is really at the heart of all modern integer programming solvers. And you guys are all about to hear the very loud train that comes through Madison every morning. So sorry about that. Okay, so I'm going to start talking about one of these methodologies for solving stochastic integer programs. That's a decomposition approach. And I'm going to start off with sort of a simpler case where we have what's known as continuous recourse. So what I'm looking at is in this case is when I look at my subproblem for a particular scenario S, I'm assuming now that all of the decision variables Y are continuous. Okay, so generally there was some continuous, some integer. To derive this kind of formulation, this approach, I'm going to assume that they're all linear. In the case of where you have some integer variables in the second stage, you can imagine that everything I'm doing at this point is just going to be a relaxation. I'll just relax that integrality and apply this technique. And later on, I'll talk about what things we need to do to sort of fix that up afterwards. So this function, under that assumption now that all the decision variables are continuous, this assumption now, or this function, this recourse function, becomes piecewise linear convex. That's something that you can sort of see from linear programming duality. So it turns out that what we can do then is we can derive cuts that support this piecewise linear convex function by solving this linear programming and basically using dual information. Okay, that's known as the Bender's approach, which I'm not going to get into all the details of that, but that's the main thing that you need to understand about that. So how does this work as in sort of a basic Bender's decomposition approach is I have a master problem where instead of having introduced that full sort of second stage formulation, what I'm doing is for each scenario, I'm introducing a variable theta s, which is going to represent the cost of my best recourse in scenario S. I have my first stage constraints, my first stage variables. But in this master problem, I'm going to just introduce a bunch of cuts. These are known as Bender's cuts that are going to be making sure that theta S indeed represents the optimal recourse value. And I'm going to derive these cuts by solving subproblems for every scenario that have this form where I fix the first stage decision variables at some candidate solution. So the way this kind of basic Bender's algorithm works is I solve this master problem. Notice it's a mixed integer program. I'm enforcing integrality. So I solve an integer program. I get this candidate solution theta hat and x hat. I take that x hat and I go and solve all my scenario subproblems that I can now solve in parallel of each other because they all decompose when I fix the first stage decision variables x hat. After having solved each one of those problems to the linear program, I use my duality to derive these cuts, and I add that to the master problem, and I repeat this process until I don't find any more cuts. Okay, so that's sort of a basic Bender's decomposition method that you can use here. And so a limitation of this basic version of the algorithm is that solving that master problem can become very time consuming. It's an integer program each time. I'm adding more cuts that tends to make it more complicated. And unfortunately, because that master problem is an integer program, it's different from linear programming. If it were a linear programming, I can kind of warm start and sort of effectively resolve after I make a small change by adding new cuts. For an integer program, if I add these new cuts, you kind of got to start over from scratch, or you can do something, but it's very limited how much work you can reuse when you resolve these things. And so that can be sort of a limitation of this basic version. So an alternative version is that you can, instead of doing solving this master problem as an integer program and repeating this process, you can instead add these Bender's cuts as needed during a single branch and cut process. Okay, so I'm going to describe that alternative now. So the second method, so I call it, say, branch and cut with Bender's cuts, is we're going to initialize, first of all, and this is an important thing I'll highlight a little more, before starting the branch and bound process, generally what I might do is solve, say, the LP relaxation of my overall problem by Bender's cuts. Okay, so I'll just relax all integrality, first stage and second stage, and do this process of solve the master problem, solve the subproblems to get Bender's cuts, and repeat that until I get no more cuts. And then I'll start doing branch and cut, again with solving LP relaxations at that master problem. And each node in the branch and bound tree, I'll solve that current LP relaxation. I'll check to see if I can prune that node. If I get an integer feasible solution, this is the step when things are different from a standard integer programming branch and bound, is because I don't have all the Bender's cuts in my problem. I might need to generate Bender's cuts to sort of get a more accurate estimation of the cost of that solution. So what I do is, even though I have an integer feasible solution, I'm not done at this node. I have to go off and solve my scenario subproblems and potentially find Bender's cuts. And if I do, I add that and resolve that node. Okay, so that's sort of a key difference here. If it's not integer feasible, then I have an option. I could still generate Bender's cuts if I want. Otherwise, I can just branch on one of those variables that doesn't take on integer values. Okay. So this step here, where I might add cuts that are going to be sort of updating the feasible region because they're sort of constraining the theta and the x relationship, those are known as lazy cuts in the integer programming terminology. Okay, so that's just something to be aware of if you wanted to implement something like this. So I want to actually show kind of an example of how this works, because it's kind of a little bit much to wrap your head around. So the first idea is remember I said I'm going to solve the master LP relaxation. So what I'm going to do is I'm going to relax integrality of my first stage variable. So I have, say, a 3-variable version of this generation expansion problem. So instead of making them binary, I allow them to be continuous between 0 and 1. And then I do this process of I solve the master problem, I get some candidate solution, then I go off and solve my subproblems, I get Bender's cuts, and I repeat this process until I don't have any more Bender's cuts. I'm only solving linear programs in this whole part here, so generally this could go pretty fast. And at the end of doing that, I have this master linear program where I have some Bender's cuts that are constraining the theta variables to represent sort of the cost of my recourse decisions. Not all the possible Bender's cuts I might end up needing, but it's some to get started. And I get this, the optimal solution is this thing, and it has this value 286.5, and it's kind of 3-variable problem I'm looking at here. Okay, so I basically solved the LP relaxation by a Bender's decomposition algorithm. And now I'm going to start doing branch and bound on top of this, because here I have these values x that are integer and I need them to be integer. So I'm going to start doing that. I'm going to sort of change in my solver. I'm going to say, hey, wait a minute, remember these are binary variables. And so the solver is now going to have to start doing branch and bound. And so given that their current LP solution had a fractional value, it's first going to branch on one of these variables. And it's going to start doing this process. Okay, so that's the branching step. Maybe it branches on variable 1, for example. It says it's 0 or 1, and then we solve the corresponding node relaxations for each of those two cases. After I do a bunch of branching, so I'm going to skip a lot of steps here. Let's imagine I have a couple of nodes where I've just fixed x2 to be 0 in one case and x2 to be 1 in the other, and higher up in the tree I had fixed x1 to be equal to 1. And the first node, that's a fractional solution. I don't have to worry about that too much. Nothing special. I could branch on the third variable, for example. But in this node 4, I have to do something special. This is that key difference from a standard branch and bound algorithm, where I have a solution x hat that satisfies the integrality constraints. Okay. So in normal integer programming, I could just sort of take this value and update my incumbent solution. But because I have to possibly add these Bender's cuts, I can't stop here. What I must do is go ahead and check to see if there's any violated Bender's cuts by solving those scenario subproblems. And if so, I add those to my master problem and resolve that node relaxation. Okay, so if I do that, these are those two subproblems that I would solve, where now I've fixed the right-hand sides in the two different scenarios according to my first stage decision was 1, 1, 0. And then different scenarios lead to different sort of right-hand sides for the demands. And so one of them actually does yield a violated Bender's cut. The other one did not, but still have to add that to my formulation to resolve. But also, having solved these subproblems, I now have a true evaluation of the feasible solution, because I know the true cost of this solution under scenario 1 and scenario 2. So I'm looking at an example with just these two scenarios. And so I now have an upper bound of 352.5. Okay, so I'm not going to go through all the gory details, but if I continued this branch and cut process to the end, what we would find is after 8 branch and bound nodes, I solved that problem. Okay, and the good news there is I was only ever solving LP relaxations throughout that process. But the bad news is, for a 3 binary variable problem, having to explore 8 branch and bound nodes is not very good. Okay, so even though this was good because I wasn't solving so many integer programs at each step of the way, it still wasn't necessarily very efficient for a 3 variable problem. And what went wrong here, and this is sort of the balance you also always have to have when trying to solve a stochastic integer program, is, okay, now I had decomposition, but I had poor LP relaxation, and so I ended up doing lots of branch and bound. Okay. So what can we do in this branch and cut method? What are some things we could do to try to improve the LP relaxations and hopefully not have to explore as many nodes? So there's actually 2 things we could do. One thing we could do is we could add Bender's cuts also at fractional LP solutions. So the way I described this model or this algorithm is I was only adding those Bender's cuts when I happened to encounter a feasible integer solution at a node. This could improve things a bit, but to be honest, I'm not confident that would improve things that much. What you're going to get better leverage out of is if you use integrality to get stronger cuts. Okay, so remember, this is that concept of valid inequalities that we have in integer programming. We want to add these inequalities into our formulation so that we get better cuts and better relaxations. And there's sort of 2 general ways you could try to add valid inequalities within this branch and cut framework. So one thing you can do is you can just look at the master problem. Remember, you have some integer variables in the master problem. We've added these Bender's cuts. That thing is itself a mixed integer program. You can try to add valid inequalities based on the information that's in that formulation. So that's the first option. The second option, which is a little bit more work, but can be very powerful in some cases, is to actually add cuts into the subproblem. Okay, so I'll talk about these 2 options in turn here. So for the first option, we have this is the master problem, sort of abstractly. We have some constraints on our first stage variables. This is kind of the abstraction for the Bender's cuts that we've added throughout this process to sort of approximate the objective function. And remember, we have some of the first stage variables are integer. So this is just a general mixed integer set and we can use any of the methodology we have from integer programming to try to get strong valid inequalities for that set. Okay, and this is just some of the examples that we have. Now, ideally, if you wanted to get the most power out of this approach, in this list of Bender's cuts that we've added, we would ideally have them all, right? But remember, in our algorithms that we're doing, we never add all the Bender's cuts up front because in many cases, it's too many to add up front. So we're adding them algorithmically. We sort of find them on the fly. And so the reality is we're only ever working with a subset of these Bender's cuts when we're trying to generate these cuts. And so this is where I get to this point of when I told you how to, I mentioned how we do this branch and cut process, I highlighted the idea that before we ever start branch and bound, I suggested that maybe it's a good idea to solve the LP relaxation by, Bender's decomposition. And then what you do is you end up collecting a number of Bender's cuts. Okay. And the benefit of doing this is because then you can load these Bender's cuts into the formulation that you then give to your, say, your commercial solver. And then the commercial solver has at its disposal the first stage constraints, but also all these Bender's cuts that you found. And then that commercial solver can go off and use all of its fancy tricks that it has for generating valid inequalities on this set and potentially improve the formulation for you without you having doing any of your own work. Okay, so this is maximizing the leverage from the commercial formulations. Okay. In contrast, if you did not add those Bender's cuts at the start, instead you just add them only on the fly as you need, then the commercial solver doesn't see those, right? If you're only adding them later, the solver, certainly can't use that to generate its own cuts, and you miss the power of its ability to generate these valid inequalities. And so in this generator expansion example that I've been going through, this sort of 3-variable one, a few slides ago, we saw when we solved the basic LP relaxation, we got the value 286.5. But if I then take that LP relaxation and give it to Gurobi with the commercial solver that I tested this with, and do nothing else and just say solve the root node, and what it will do is it will generate some valid inequalities based on those Bender's cuts and knowing that those first stage variables are binary, Gurobi was able to improve that root node relaxation all the way up to 326.8. And the optimal is 352. So that made a big difference in terms of the relaxation already just by loading those Bender's cuts into the original formulation. Okay, so the takeaway of that is that kind of, I call it phase 0, where somehow you initialize the formulation, maybe by solving the LP relaxation or by solving the subproblems at various heuristically generated solutions. So you generate a list of these Bender's cuts to start with, load those into the formulation, and the commercial solver you use might then be able to use that to improve the relaxation a lot. Okay, so that's sort of almost for free, you can get those improvements. Okay, so the second part, which is it's less free, is to add cuts within the subproblems itself. And so the idea here is for a given scenario, you have this sort of set of constraints that include the first stage constraints, but also the constraints that link the first stage and the second stage, again, for that given scenario. So here I'm just plugging in the data for a particular scenario S. So for every scenario in our model, you can imagine we have such a set. And it turns out that if you can derive valid inequalities for this set, then you can add those into your Bender's subproblems and improve the overall relaxation as well. Okay. So here, I'm emphasizing here that when I define this set, I'm going back to the case where some of the second stage variables Y can take on integer restrictions, because this is a situation where adding these kind of subproblem cuts, as I might call them, is very, very useful, especially when you have these integer recourse decisions. And even though we've only seen an algorithm, this Bender's algorithm only works if we have continuous Y decisions, we'll see how we can extend that in a little bit when you have integer decisions, or in various cases what you can do. And this is a huge area of research, generating cuts based on these scenario subproblems, and then adding them to the subproblems and improving the overall relaxation. This is, this is just a small sample of many of the papers that have explored different ways to do this in very clever ways, and improve that. So this is sort of, summarizing a huge area of research in the stochastic integer programming field here. So just a few of the references that have followed this particular approach. But the key thing I want to emphasize here is what we're doing is generating these valid inequalities for a single scenario set. And the reason we constrain ourselves to generate valid inequalities for a single scenario set is because then we can still apply this Bender's decomposition framework. Okay, so it keeps us in that decomposed frame. Whereas if you generated valid inequalities that were across multiple scenarios, you wouldn't have the same decomposition anymore. Okay, so how does this work? Okay, so we have this kind of master problem, subproblem sort of action happening again. We solved the master problem. Now let's say it's a linear program relaxation of that. We get a particular fixed solution, say theta hat and x hat. We send that to subproblem S. By solving that subproblem, remember we could generate Bender's cuts. So here I have relaxed integrality there, and we can generate that to the master problem. Okay, so that's kind of the basic Bender's framework. With these subproblem cuts, we extend that after having solved the subproblem. When we got now a solution y as for that given x hat, we then say, oh, can we find valid inequalities for that scenario S set that would cut off x hat, y hat, s. So we do this integer programming valid inequality separation step, and we generate cuts that we then add to subproblem S. That's this kind of block here. Okay. So now this kind of extending that subproblem S, but remember, it's still a linear program. Even if these cuts we generated were based on integrality of some of these y variables, we add these cuts, and now we've ignored the integrality again. So by solving this linear program, this enhanced linear program, we can then get a new Bender's cut that we add to the master problem that's going to improve the relaxation even more. Okay. Now, one thing that's really counterintuitive here is even if my first stage variables are integer, but my second stage variables are all continuous, it can still be valuable to do this, because when I separate cuts, I can use, even though x hat was fixed, my cut separation can still use the fact that x hat was supposed to be an integer variable, and I can derive cuts that I can still add to the subproblem. Okay, so this is sort of a counterintuitive thing that even when x hat is fixed, it can still be useful to generate these cuts at these subproblems. Okay, so that's how that process works. And so, how do we generate inequalities for these individual scenario sets? How does that bottom step work in that figure? Again, you can use general purpose mixed integer techniques. So, this is where, implementing this might be more difficult, because you might have to start from scratch in implementing some of these things for that step in here. But also, again, this is where if you know something more about your problem, you can really take advantage, and you can use problem-specific cuts or build up a better formulation that's sort of like having this valid inequalities at that bottom step. Okay, so I'm going to go back to that facility location problem again. And remember, we derived for that problem these valid inequalities. It's a small list, right? So we can just add them to our formulation rather than adding them as cuts. Okay, so we have these valid inequalities, and let's see what happens if we add those to the formulation in this case. So we can do that branch and cut process again. Again, we get our initial sort of master problem formulation. I think I'm going to skip these iterations, but we do these Bender's cuts. Actually, the one thing I want to show is highlight here is when I solve the subproblems. Now, within the subproblem, I'm including these additional constraints that were those valid inequalities. Okay, so that's the key thing I change is I change that linear programming subproblem. And so what that's going to change, ultimately, it's going to change the dual solution that I get, and it's going to change the Bender's cut that I'm able to add to the master problem. And it's sort of not obvious to see it here, but turns out that those Bender's cuts become stronger and lead to a better LP relaxation. And so remember, when I solved the original LP relaxation, I got a value of 286.5 in this example. If I use this new formulation that was very simple, it's just these very simple additional valid inequalities, and I just added them to my Bender's subproblem, my bound improved to 332. Okay, so that's already a big improvement. Remember, the optimal is 352. And then if I take that formulation and combine it with this other idea of adding cuts in the master thing, and let the Garobi, the general integer programming solver do that for me, on top of that, we get now a value of 350.5. It's very near the optimal solution, and I haven't done any branching at all. This is all purely based on cuts and improving the formulation. Okay, so it just illustrates the potential value that these techniques can have in terms of improving the bound, then ultimately we hope that that reduces the number of branch and bound nodes that you would need to solve. Okay, so I'm going to recap here for these problems that have continuous recourse. At least we have kind of now these two options for how to solve it. First one is we can solve sort of the Spender's approach, where the master problem is itself an integer program. We'll just repeat that process. The second option was this branch and cut approach, where we integrated the addition of these Bender's cuts and maybe these other cuts based on integrality into the branch and bound tree. And so, there's these two options. Which one is better? Well, there's kind of pros and cons. So that first option is certainly easier to implement, and it tends to solve, fewer scenario subproblems. So you have fewer iterations before you converge. And so if solving a single scenario subproblem is very, very time consuming, this might be the way to go. But the disadvantage is that that master integer programming problem might become very slow. So you might sort of get stuck with that. Whereas in the branch and cut approach, you're only ever solving these LP relaxations as part of one overall branch and cut process. So that's the advantage. You can exploit sort of subproblem cuts and things like that, but it's certainly much more difficult to implement. Okay, so that's kind of the trade-offs between these two different approaches. And my advice on this is start with option one, right? Because actually first start with the deterministic equivalent form. If that fails, then start with option one, and only if that fails, try option two, because that's certainly the most difficult to implement. Okay, so what about this case, which I've sort of brushed under the rug up till now, where I have in some of my subproblems, my recourse decisions, some of the decision variables must take on integer values. Okay, so in that case, things get much more complicated, because this QS thing that I was previously approximating with Bender's cuts is now the value function of a mixed integer program, which is a very, very ugly thing. Okay, so first of all, we can just relax integrality, and we get these Bender's cuts from the LP relaxation, and so those are valid, but they're not going to be any more sufficient to enforce the key thing we need in the master problem, that the theta s should be greater or equal to this, so that we get to convergence of the algorithm. Thanks for the reminder, Walter, on the time there. So in terms of how do we get to a convergent algorithm in that case, it turns out, it's naturally much more complicated. And so really, there's been a whole lot of research on dealing with many different subcases for how do you enforce that constraint. That's the key thing. Somehow you need to enforce that constraint at the end of the day. You can do that by specialized cuts or specialized branching. And so there's many different things, and I won't get into the details, but just kind of put some references here. The main thing I want to highlight is that for all of these methods, so whatever, your specific structure, whichever case you're in, you need to adopt one of these methods to get to a convergent algorithm. But whatever is the method, this idea of using these master cuts and these subproblem cuts to improve the relaxation will be useful no matter what, because it can improve the relaxations you're solving, reduce the number of branch and bound nodes, and help the overall thing. So you need, these master cuts and subproblem cuts aren't sufficient for any of these cases when you have these integer recourse, but they're always going to be helpful in all these different cases. Okay. So the different cases, there's special things you can do when you have pure binary first stage variables. Very nice work if you have pure integer first and second stage variables. If you have mixed binary first and second stage variables, there's certain special types of cuts you can use to get convergence in that case. If you have pure integer second stage, there's certain reformulations of branching you can do. And really exciting recent work here is the most general case, general mixed integer in both cases. There's Ward Remainders and his student, I jumped way ahead somehow. Oh, that was to the reference there, excuse me. They have this really nice work there where they actually combine somehow cuts from the master problem into the scenario subproblems to yield sort of convergence in this most general case. Okay, so in just a few minutes, I want to just kind of highlight in a very abbreviated version another approach to solving these things. So everything I talked about so far was kind of branch and cut. We're solving LP relaxations. So a completely different approach, something known as dual decomposition, where instead of using the LP relaxation, we're instead using some sort of a relaxation that's based on solving integer programming subproblems, but single scenario integer programming subproblems. Okay, so this goes back to the classic work of Perot and Schultz. and is implemented in some modern solvers. So the basic idea of this framework is we're going to create a decomposition of our problem in a different way other than benders. Okay, so the first thing we're going to do is we're going to create copies of our first stage variables for every scenario, right? So we have this one set of variables X, right? That's supposed to be the same set of variables no matter the scenario. What I do is I create copies. I say, let's let XS be what I do with scenario S, okay? And so everywhere in my formulation where I had the variable X, now I put in the variable XS and I repeat those constraints for all scenarios. Okay? Now, of course, we're not allowed to actually have a different first state decision for different scenarios, right? They actually should all be the same. And so what we do is we add explicit constraints. They're called non-anticipativity constraints. It's the hardest word to say in stochastic programming. But they basically say that all these copies of the variables that I created, they should all be equal to each other. Okay? And you can do that in different ways. This is one way to do that here, where I just say, for each scenario S, that should be equal to the average of all the other scenarios, including itself. That's one way to do this. Okay. So what you do, though, is then we have these constraints, and they're kind of complicating things because they're the things now that link all the things together. And what we do is we apply a technique from general integer programming known as Lagrangian relaxation, where we take those constraints and we sort of move them to the objective with kind of a penalty. Okay, so we have parameters lambda, which are sort of the penalty parameters for moving those non-anticipativity constraints into the objective. And I create a relaxation problem because now I'm no longer enforcing those constraints. I'm instead kind of penalizing them with these parameters lambda. And if I solve this problem, it's not hard to show that it will give me a lower bound. So this is a different way to get a lower bound in the true stochastic integer program. And it turns out that I can evaluate this lower bound by solving an integer program for every scenario independently. And that's kind of what this looks like. I'm skipping the details of this, so hopefully just follow the high level of this. And by, so I solve a separate integer program for every scenario, where in that scenario, I have sort of the data for that scenario, and I've modified the objective in a particular way for that scenario. That's what these things look like. So I take my overall stochastic integer program and I decompose it into a deterministic integer program, one for each scenario. And so then what I can do, this was all for a fixed value of these kind of dual multipliers for doing that relaxation. And then I can define a Lagrangian dual problem where I say, let me find the best value of those multipliers over a certain normalization condition. Don't worry too much about that, but basically just saying, find the best bound I can get from this approach. Okay. And it turns out that this approach tends to lead to a dual that, in general, may not be optimal. It's still a relaxation, but tends to be, it's always at least as good as the usual linear program relaxation, and tends to be a very, very good relaxation. In almost every instance class I've seen, the value of this Lagrangian dual, if you can compute it, is very, very close to the true optimal integer value. Okay. So there's a big if there is, how do you compute that? Turns out to be pretty hard to do. Okay, so this is a maximization problem over now these lambda, these kind of dual decision variables we're trying to choose here. It's high dimensional. It's concave in maximization, so that's good news. But because it's high dimensional and you have to solve a large number of, an integer program to evaluate this each time, it tends to be difficult to do. So it's convex program, but evaluating subgradients of this thing requires solving integer programs. So it's challenging. Okay, so all I'll have time to say here is that, there's a lot of interesting research, including some that I've done recently with my student, but other groups as well, in terms of methods for how to solve these Lagrangian dual problems more efficiently. The last thing I want to just highlight, though, is this kind of recent trend, some interesting ideas, is how to actually combine this idea of this Lagrangian dual with this branch and cut approach. Okay, so remember, this Lagrangian dual has a very, very strong bound, but it's very difficult to compute. And so the idea is maybe we can try to get the best of both worlds, where we're going to try to do like a Bernder's branch and cut based approach, but start to integrate some of the things you might do for solving these dual decomposition problems to generate even stronger cuts within that benders branch and cut approach. Okay, so there's some very interesting work that's been done along those lines, and with my student Ray Chen, we did some additional work. And this paper I mentioned with word remainders fits very well into that framework as well, where they are sort of using this strength of kind of these dual decomposition idea, but within this branch and cut approach. So I think there's a really exciting new direction for this area. Okay, so I did kind of rush through those last few slides, but I finished close to on time. And so just to kind of wrap up here, basically, I'm super exciting. Like, there's lots of important applications for stochastic integer programming, and there'll be more as we improve our ability to solve these problems. And in terms of that, we're making significant and steady progress in the methodology, but there's still work to do, right? So unfortunately, I would say, solving stochastic integer programs is still not routine, right? So in the world of integer programming, you almost can say solving integer programming is now routine, in the sense that most people take it for granted you can solve a reasonable size integer program in enough time. But I wouldn't say that's the case yet for stochastic integer programming. So we have work to do. And I would say this even applies in that case, which seems simpler, where you have continuous recourse. Even still, some of those problems can be hard. One of the things that I find, a need for our community is to expand the size of our test instances. So we're still sort of, many of the available, at least publicly available test instances are sort of too small to be sort of that interesting for showing that we can solve real world size problems. So I think that's something that we need to work on. And finally, I didn't mention anything in this tutorial about multi-stage stochastic integer programming, and that's really, really hard. So that class of problems remains very challenging, and there's all kinds of interesting research to do, and even just getting approximations for that class of problems. So I'll stop it there, and I'm welcome and look forward to questions.
So thank you very much, Jim, for the very nice tutorial. So let's open the period of Q&A. So again, just recalling, you can either raise your hand and use the Zoom raise your hand option, or you can write your question directly in the chat, and I'll go through the list. So are there any questions? Oh, there's one from Maximilian.
Yes, hello. First of all, thank you for the great tutorial. I would be interested on your opinion about, because you're talking about all these sophisticated methods on finding better cuts and solving larger and larger problems. What is the approach on like finding a better set of scenarios so you don't have to actually solve such a big problem, because you reduce your search space to the relevant scenarios to get a good approximation?
Yeah, that's a very good question, and at the beginning, I sort of very quickly walked over this idea that you can use sample average approximation and replace the expected value thing with a list of scenarios. And the naive approach there is Monte Carlo sampling, and then you just sort of run with that. But absolutely, there's a whole other very interesting stream of research is to say, well, rather than doing naive sampling, let's create these scenarios much more cleverly, such that you can hopefully solve a problem that needs not nearly so many scenarios. And in that case, all that decomposition stuff isn't so necessary. You can just take that problem and give it to your integer programming solver, and there's a good chance it'll solve it for you. So that's certainly an alternative approach. If you're able to sort of create this smaller set of scenarios that approximates your problem well enough, then that's a another way to go.
So there was another question by Ian.
Hey, Professor, great talk. Gave me a lot of things to think about. My question is also a bit more on the like a philosophical question, but just at the beginning, you also, like the previous question, you talked about how when you're taking sample average approximations, in most applications, you don't need that many samples. You're favoring kind of tractability, and it's also because kind of the distribution from what you're sampling from itself might be an approximation.
Yep.
So using this intuition, I was just thinking about, with the same intuition, could I say that using that same intuition, could I also think about the fact that would I really need to solve these problems to optimality? So would I actually need exact algorithms, or would it suffice to have algorithms that can quickly get me to good solutions?
Yeah, I think that's, I mean, definitely a great idea. I mean, you know, the challenge that anytime you get to like, you know, some sort of a heuristic algorithm, basically that becomes then, it's just always, you know, at one point do you understand that you're getting a good enough solution? And so, you know, so if you can, you know, somehow verify that and have confidence about that, then absolutely that's a very, very useful approach. But that's kind of the limit of that approach, unfortunately. And you know, one thing relating to this whole question of evaluating scenarios, and just expand a little bit about that sample average approach that you know, I didn't have time to get into. But one thing that's nice about the sample average approach, even with the basic Monte Carlo approach, is you can do sort of replication. So you can solve with multiple different samples, and based on that, you can build kind of statistical estimates of the true optimal value if your you know, sort of model were correct. And so in that sample average approach, so even though I didn't get into the details of it, that has built into it a mechanism for understanding how good is your approximation. So it's not just purely approximation, it actually has a way of estimating the error of your approximation. At some cost, you have to do replication in order to do that. And so that's, you know, an advantage of that particular approach. And so, you know, with other, you know, approaches as you develop approximations and things like that, that I think would be the key interesting thing to explore is, you know, how can you maybe bound the error or things like that, or in what, you know, circumstances can you understand that the approach will lead to good solutions.
Perfect, thank you.
Thank you. So are there other questions from the audience? Utsav?
Hi. Hi, thanks for the nice presentation. I have a question regarding the modeling. Like here it is, from what I understand, the problem is that the first state decisions are not related to the uncertainty. I mean, it's assumed as far as I understood. But if I open a facility and opening that facility changes the demand. So is there some work going on in this literature?
Oh yeah, this is a very, very interesting question. And so the term for that is what they call decision-dependent uncertainty. And so that's a situation where your decisions actually influence the randomness. And you really caught a good subtle point about the model as I wrote it, is I'm assuming that's not the case, right? So the classic two-stage stochastic programming model assumes that the decisions are, you know, the uncertainty is independent of the decisions you make in the first stage. And so, you know, in terms of how do you solve that, that is an active area of research, and there's different types of decision-dependent uncertainty. Some things relate to just whether or not, you know, you observe certain random outcomes, like if you install the sensor or not, right? That can be something that influences what you observe. Or, you know, it could be, you know, a matter of, yeah, if you open facilities, then, you know, clearly it could be the case that if I have, you know, a lot of, like, if you think of like stores or something, and you're locating those, if you put a bunch next to each other, then the demands are not going to be the same, right? You're going to be influencing that. And so, you know, there's, you know, that's a, you know, it's a different problem class. It's more difficult generally. One thing that you can do is, I mean, the kind of classic approach, the way, you know, your first attempt for such a thing would be to try to remodel it in a way such that the uncertainty is external again, right? So maybe you can create a model in this case of the customer, you know, I'm locating stores, and the customer demands somehow depend on the locations of the stores. Well, maybe I have some underlying model where I understand the relationship of the stores to the demands, and then there's some external random thing, and you could try to build that in. typically such a model might end up being nonlinear, unfortunately. And so then you have to deal with a mixed integer nonlinear program that's stochastic. But that's kind of the first thing to do. It's just kind of, just look at it more and try to, build into your model that relationship, and then there'll be some external randomness. But otherwise, if you really do have this model that connects it all together, you need a different solution approach. Good question.
So there was another hand raised, Shannon.
Thank you very much for the inspiring talk, Professor. I got a question, probably something that I didn't understand it completely. So for the cuts that we can add for the second stage problem, is it only for the case that we have integer in second stage problem as well?
Oh yeah, thank you for asking that question. That's a very subtle point. Go back to that figure here. So the answer is no. So as long as you have integer constraints in either the first stage or the second stage, this framework can be helpful. And the reason for that is when I go to separate cuts at this bottom level here, what I'm doing is I'm separating cuts for that set. And if I go back to the previous slide here, that's the set of feasible solutions for scenario S, where my decision variables are both the first stage and second stage variables. And so if I have integer constraints on the first stage variables, even if the second stage is all continuous, I can still hope to get interesting valid inequalities for this set. And those I can add as sub cuts at this subproblem stage. And I've done research in the past with Merva Bordur on particular applications where this was the case, that the top level problem was integer, but the lower level was pure continuous. And yet we found great value to adding cuts at that stage in any case. And then you get these better Bender's cuts.
Thank you.
Thank you. So are there other questions? Still have a little bit of time, guys. Oh, there is one in the chat, or two actually. One from Raphaël Boudreau. Are you aware of work using other solving modeling paradigms such as constraint programming?
Yeah, so definitely. I mean, in a certain sense, this broadly is a search process, right? The branch and cut. It's like then it's sort of it's a search process. You're subdividing the feasible region. And in this case, the way we're solving, the relaxations we're solving to kind of process nodes is linear program relaxations. But yeah, absolutely. If you have constraint programming there, you can use, propagation things instead at that level, and avoid, sort of things there. So I do think that this is it's an approach that you can apply in this area. I don't know much about it, personally beyond that.
Good. Are there other questions? Ian, another one?
Yeah, just a question about kind of your experience in working in different applications, just about modeling the recourse. Like in the example that you gave with energy generation, the uncertainty in the parameters could be defined over a day, over a week, over a year, over multiple years. So just in the applications you've worked on or in your experience, how do you actually define a suitable recourse problem and a suitable definition of uncertainty?
Yeah, it is that. I mean, it's a real modeling challenge, right? So I mean, it's hard to provide a general answer to that, other than to sort of affirm that it is a challenge. I mean, and it's something that you have to have, I think, good problem insight about sort of capturing what is the key sort of feature you need in there. I mean, the one I'd say just general principle to keep in mind in these types of problems and thinking about what you're going to build into that recourse model is that the key purpose of the recourse model is not to, of course, to model every detail of what's going to happen in the future, because that's infeasible. You want that recourse model to provide a good guidance of the value of your first stage decisions, right? And so that's, I mean, that's the principle to keep in mind. And so, and then, well, what does it mean to be good guidance, right? That's kind of, hard to define essentially, but that's, I mean, the goal anyway. And you have to kind of, as a modeler, strike the balance between providing good balance or good guidance and being tractable, right? At the end of the day, I mean, you could try to, write a model that, hourly for the next 10 years. And that's very detailed and accurate in some sense. But it's hopeless to solve. So somehow, you have to find that balance.
That's very helpful. Thank you.
And I would add the other part of the balance here. I mean, it's not just about the problem size becoming huge, which would also be an issue, but also about like, what can you model in terms of the uncertainty, right? Maybe you only have a good, way to predict at the weekly basis, what's the whole demand. And then, maybe that makes sense to build a weekly model or something instead.
So there are two other questions from the chat, and maybe we can end it there for today. So a question from Atem Benamor. So how do Bender's decomposition-based approaches compare to multi-stage column generation-based approaches for stochastic optimization?
Multi-stage column generation. I'm not sure what is meant by multi-stage column generation. So I maybe you can explain that a bit, Atem?
Hello.
Yeah.
Guys, so thank you for the presentation. My question is that because I saw several models before that in each stage, when they solve a stress form, they have several stages where they do conjugation in every stage. And then sometimes they relax integrality, sometimes in the first stage, sometimes in the second stage, etc. So that's kind of approach. And then my question is especially for that the fact of having integrality requirements in both the master and the recourse problems.
Yeah, so I apologize if I don't quite answer the question because I might not be exactly familiar with which work you're talking about. But I mean, there are works, and it kind of relates to this Lagrangian decomposition thing that I went through very quickly at the end, where you can sort of build into your model in kind of a column generation framework, implicitly deciding what I'm going to do now and in the next stage. And you have sort of a decision variable that sort of maps that whole thing. And then you would need column generation to solve such a model. And typically what the value of the model you would end up getting is like this Lagrangian dual. You can almost think of it as a different way of solving that Lagrangian dual problem. And then you would have sort of a similar kind of challenges and how do you solve that. But certainly you'd have the similar benefits also of having a good relaxation. And so if, I mean, if I'm understanding well, I think it kind of relates to that second part of Lagrangian dual where you get potentially stronger bounds, but challenge in sort of solving those relaxations becomes the thing you have to address.
Okay, thank you very much.
Sure.
So maybe
and then, yeah, I read that one there. So it's not about this. I knew somebody would ask about distribution of robust. Yeah, I mean, so obviously, it's well motivated, right? I already mentioned about the fact that, you probably don't really know the distribution of these random variables exactly. So, doing something distribution robust to kind of protect against the error in the specification of the distribution makes a lot of sense. It's, for these two-stage problems where you have the recourse, responds to that. I mean, it's an ongoing area of research. I know of some sort of groups that are working on methods for that. It's challenging though. I mean, so that's, I mean, it's I would say, in some cases in distribution robust optimization, you get kind of this win-win where, okay, you're robust and somehow the formulation works out nicely and it becomes, nice, easy to solve. Unfortunately, I don't think this is one of those cases. I think the distribution of robust formulation is not necessarily easier to solve than the classic stochastic integer program formulation. I mean, it remains to be seen. Maybe, you know, there will be successful research there, and it will become easier to solve. But I think, you know, the still remains to be determined. So, yeah, this is exciting future directions to explore.
Okay, so thank you very much, Professor Luedtke, for the tutorial.